Today we are going to start with response analysis. Response means how a particular system respond to a particular input, right? And what output it will give. It is the output is response of the system to the input. Now response analysis are two type of analysis. First one is time response analysis, and second one is frequency response analysis. Right. So first of all, let's see. Input can be of any random nature. It can be like in general we deal random kind of input, but to test a system we generally take standard inputs. Why standard inputs? Because any input can be represented in terms of these standard inputs. Generally, not like very exactly, but approximately we can generalize our input in terms of these standard inputs. That's why we take standard input, also called test signals, right? So test signals we use to determine the characteristic of the system and what is the response of the system due to that particular test signals, right? Let's see what are the test signal. Generally, first one is impulse. You might have studied in your signal and system course, and if you haven't studied, let me brief about impulse. Impulse is like is a direct function we take, and it is represented as this, and with area 1. This is what? Minus infinity to infinity del t dt is equal to 1, and it is equal to 0 when t not equal to 0, and not equal to 0 when t is equal to 0. This is our delta Dirac function, or we call it unit impulse function, or simply if its area is something else like a, it is impulse function, simply an impulse function. What impulse function implies? Impulse function implies a sudden shock, like suddenly this is going like this, going like this. Actually, talking in practical sense, it is not possible to generate an impulse, but a shock can be of very finite, very small duration. Then that can be approximated as this impulse function. This belong to a shock input. Whenever we have a shock kind of input, then we can check that system by using impulse test signal, right? And second is sudden change. Sudden change is like sudden change, like say any system is steady with respect to input, and suddenly a step is there, and it changes like this, and suddenly a step is there like this. So this kind of sudden change is basically represented by a step function we use. Step function is used to determine the properties of the system whenever there is a input which has sudden change. So input may be anything, like this kind of input may be anything, but since it has sudden change, so we can use it as a step function as to test a system, how this system will respond to these kind of signal, right? And third kind of test signal, we have a ramp function. Ramp function generally we define as, sorry, I haven't put ut. Step function is represented by ut, and ut is this function, ut with respect to t. This is our unit step function, or simply step function. If step is more than 1, like 2, 3 or half, anything it can be, then it is abbreviated as step function. If step is 1, then it is abbreviated as unit step function, right? And third one is ramp function. Ramp function is denoted as rt with respect to t, and this is represented like this. How this is this represent how it represent that a signal is changing steadily, right? So it is called constant velocity type. Constant velocity type. Whenever we have any signal which is constant velocity type changing like this, then we can use ramp function to test that signal, right? And fourth one is acceleration function. Acceleration, or constant acceleration constant. In that case I can use a parabolic function. Parabolic function we know, like this kind of shape, right? This is parabolic function. So these are the very general. There can be other third order or fourth order of inputs, but generally we use these kind of input, and these are very basic test signal. By using these four signal we can generalize any random input in terms of these inputs. Not exactly, but approximately we can know the response of the system. And fifth kind of thing is there may be oscillation in input, like oscillations. Whenever there is oscillation, then we can use our standard function, sinusoidal function. Sinusoidal, it can be sine or cosine. We know sinusoidal function are sine and cosine. So if I summarize these four things, these four our test signal come under time response analysis, right? And these this kind of where we use sinusoidal input as test signal, and input signal is generally oscillating type, and we are defining the response of the system using sinusoidal signal. These are called frequency response analysis. Frequency response analysis, right? So first we will be discussing our time response analysis, then we will go to frequency response analysis. And now let's start with first time response analysis, right? So first of all we should understand there are type of system, like what kind of, like first order. It can be of first order. Why this is called first order, it will be clear very shortly. First order, second order, or maybe third order, or maybe other higher order. Generally we will discuss about first order and second order, and third order and other higher order can always be broken up into second order and third order. First order. Third order can be like second order plus first order, right? And fourth order can be represented as second order plus second order, or first order plus first order. First order plus first order plus second order, but it cannot be represented in first plus first order plus first order plus first order. No, this is wrong, right? This will be clear as we will proceed with our analysis of our first order and second order. Now first of all we will start with our first order system. First order system. right? So first order system, there can be a different kind of system doesn't mean any particular we will generally deal with our electrical system, but that is not the only system. There are other mechanical system also that we will see very shortly. This part is not in gate, but in ES this is there, so we will also look at this mechanical system. And there can be other system, hydraulic system. We will not deal with this system in our this course. And there can be pneumatic system, and there can be thermal system. Thermal system is like heating of water and temperature in furnace. Those kind of system are thermal system. Pneumatic system can be there, hydraulic system can be there. Generally we will deal in electrical system. And mechanical system may be like this. This is a spring and this is a damper, like this is our mechanical system. A hydraulic system can be like a tap and filling this water tank. This can be hydraulic system, right? But we will talk about in electrical system. Mechanical system we will see in brief, but for gate purpose this is very important, right? So first of all, let's see our first order system. First order system is like this, R and C. This is very simple. RC, low pass filter, V0 and Vi. Why I have taken this low pass filter? First of all, this can be high pass filter, you may ask, but that is not the case with control system. Generally control system our low pass system. Why low pass system? What do you mean by low pass system? First of all, low pass system are those system which can pass only low frequencies only. But why not high frequency? We don't use high frequency in control system, because at high frequency means bandwidth increases. Bandwidth increases is one of the good factor in communication, but with bandwidth increase, noise also increase. We are not bothered about communication bandwidth here. We are bothered about our accuracy of the system. Like if noise is increased, then there is no meaning of controlling. Control system is what it is, controlling something. But if it is we have mentioned in its definition itself that we need to manipulate our output as per the desired. But if noise is increased, output may not be required output may not be obtained. That's why we don't use high pass filter or high pass system in control system. We don't use, we generally use low pass system only, right? So this is very basic low pass filter, RC filter it is, and this is output, this is input. Or in general term, in our block diagram reduction and in signal flow graph, we have used output as like CT and input as like RT. So we will not lose generality and we will use those symbols only. So how can I write our CS? CS is our output is RS multiplied by 1 by SC on R plus 1 by SC, right? So CS by RS is nothing but transfer function. We want to know the characteristics of the system with respect to different test signal, right? So how I can write this? 1 upon SC R plus 1. Now here RC is time constant. RC is time constant, and generally represented, we will represent it as T, and it also represented as sometime tau. right? RC is time constant. Actually, why it is time constant? It defines how much time any transient take to charge this capacitor, like whatever be the desired tolerance, that we will take into account, that we will see very shortly. And if you have covered network theory, then you might have understood why this is time constant. And if it is time constant, it has the unit of seconds. If you are not familiar, sometime in interview they may ask question why its units are seconds. So you need to have understanding of network, and after solving those things you will get like some equations is something, and e to the power minus t by t. So this thing, exponential power has to be dimensionless. When this is t in second, then this t also has to be in second, right? So this thing you will study in your network theory. I just brief about it. So I can write CS by RS is equal to 1 by ST plus 1, where T is equal to RC, right? This is general first order transfer function. Whenever we have asked first order transfer function, we will use this standard transfer function only. So let's start our analysis with our first test signal. First we will see impulse response means my input is impulsive, RT is equal to del T. I am taking here unit impulse. It's not necessary, but for the analysis purpose and for simplicity I am taking a unit impulse only. Now if I take Laplace RS is equal to 1, del T has its Laplace is equal to 1. Let me brief about that. Fs is like Laplace of this RT, say some function, and it is defined as minus infinity to infinity del T e to the power minus st dt. When you put this del T, because del T is equal to 1 at t equal to 0, this is not standard, but so Fs will be equal to 1. That's how we obtain this thing, right? So Rs is equal to 1. Now we have first order transfer function as Cs by Rs. Rs is nothing but 1 upon St plus 1, right? So I can write it as Cs is equal to 1 upon St plus 1, right? So what I can do, I need to identify its time response analysis. So let's do some manipulation and write it in terms of standard form, T s plus 1 by T. Now from your signal and system understanding, I am directly taking inverse Laplace transform. When I take inverse Laplace transform, this represent Ct is equal to 1 upon T e to the power minus T by T into ut. I am taking for causal signal, because non-causal signal are not reliable, and I am talking in terms of a practical system. So I am using ut with it, right? So this is called impulse response of first order system. Now I can plot its behavior. I can plot its behavior with time. So like this, impulse response, impulse response I denote it by IR with respect to t. Now at t equal to 0, it is my 1 by t, right? And 1 by t, and fall will be exponential. all will be exponential, and as t tending to infinity, this will tend to 0, right? So what now what our impulse response signify? Why first of all, why impulse response is so important? When impulse response is what it describes the natural response of the system, right? So impulse response represent our natural response of the system or transient part of the system. We are not getting steady state, right? It's like transient of the system, defined by impulse response, right? And one more thing, why impulse response is so important? Impulse response tells us the response at all the frequency, right? Why impulse response is like this at t equal to 0, right? So this is del t, but when I am taking its Fourier transform, it is coming 1. Fourier transform or Laplace transform are both are the almost same thing, not the same thing but almost the same thing. You will understand the difference when you will cover those things in your signal and system course. If you have already covered, that's good. As just understand that this is Fourier transform of del t, right? So it tells us the it is 1. So Fourier so impulse response tells us the response of the system at all the frequency. That's why it is one of the very important thing in our network analysis or in control system or in signal and system also, right? So and what it signify? It signify that a transient is dying out exponentially, and as t tending to infinity, transient will die completely at 0. But generally we don't wait for infinity time, we take some tolerance. Here it is almost 0, so maybe some 5 time constant, or maybe some generally we take 5 time constant. Sufficient transient will be decayed by sufficient amount in 5 time constant. Only 2% of tolerance will be there, that we will see very soon, don't worry. Now what else? One more thing, like I am taking this s plus 1 by t, and if I draw pole location, so minus 1 by t is here, right? So I am getting a decaying response. But if I have a pole in right side, then I'll be writing s minus 1 by t, and it will be e to the power t by t ut. Now if I take response will go like this. This is not the response required by any system, because if it is making like this, if it is responding like this, that means this system is going to give infinite. So this is not acceptable in our control system. Control system needs stability. So any system can be defined as stable if its impulse response is less than infinity, right? It can be finite, it need not to be 0, but it should be decaying, or it should be less than infinity with when I integrate the whole impulse response. So a system is stable if its response we take 0 to infinity for causal system, and magnitude of impulse response and dt, it should be less than infinity, right? Its impulse response should not be, this is very important thing, and you should be very comfortable with this. Why this is why this should be less than infinity, so as to a system is stable, right? So next we will look at what is time constant, how time constant is defined in terms of our first order system, and in impulse response how we will define it here. What is one time constant, that we need to define. right? So what we do is we take a tangent here. Why I am taking tangent, it will be very clear very shortly. So let's take, this is the impulse response, let's take its derivative dct by dt, right? So let's denote 1 by t with a, e to the power minus t by t ut, right? A, why I am taking a, this is nothing but gain, right? Sorry, not the DC gain, but I'm representing it as a. Now a minus 1 by t e to the power minus t by t, right? So what I do, I'm taking I want to know its slope at t equal to 0. At t is equal to 0, dct by dt is equal to minus a by t, right? So how do we find this thing? Let's say this is x and 0. So how do we define slope? As 0 minus a by x minus 0, right? That's how we define slope. y2 minus y1 upon x2 minus x1 will be equal to minus a by, so these both will cancel out, therefore x is equal to t, right? So x is equal to t, right? So let's represent this point, x is equal to t. Let me take it as in on new page. This is our impulse response. This is impulse response, not CT, impulse response, right? And here it is a, will go like this, and I have taken, sorry, not going to 0, this is like I have taken tangent here, and this value was t, time constant, and I want to define the impulse response at this point. Now we have impulse response, I have a e to the power minus t by t. Put at t is equal to t, impulse response will be equal to a into e to the power minus 1, or 0.37 a, and 0.37 a. It is, it falls by 63% in one time constant, right? So if I have to define time constant in its first order system, time constant is that value of time, or time constant is defined as time taken by impulse response of a system, time taken by impulse response of a system to reach to 37% of its initial value, or to fall by 63% of its initial value in one time constant. Either it will be for 63% fall of initial value, or 37% of its initial value. We can define in both way. That's the definition of our time constant. And what is this? If transfer function like 37% of its initial value. Let's now example, like we have a transfer function a upon s plus alpha, right? So I can write it in terms of time constant form. A by alpha is equal to s by alpha plus 1, right? I can write like this. And so what it is, time constant is equal to 1 by alpha, and therefore, or we can say time constant is inversely proportional to pole, right? So if pole is far away from imaginary axis, then time constant will be less and transient will be die out very rapidly like this, right? And say A position, and if it is B position, then time constant will be more, like this will go, curve will go this, and if it is at this location, this curve will go like this. So as pole is approaching to this imaginary axis, then our transient time are taking more time to decay, right? So what is time constant is nothing but inverse of the pole in its first order system only, not let's complete our discussion of our impulse response. So what is more important? Two things are very important in this impulse response. That impulse response is complete response of the system, because it gives the characteristic of a system at all the frequency. Second thing is, a system is stable if its impulse response is absolutely integrable. This is called absolutely integrable, right? And this thing and third thing was very important, that what is time constant definition in terms of its first order system. Time taken by the system, time taken by the time taken by impulse response to reach to its 63% of initial value, or fall by 63% or 37% of its initial value. And fourth thing, time constant is inversely proportional to pole of the first order system. That complete our discussion of impulse response of first order system, right? So second we will see step response, right? So what it is, input is RT we define, and UT, right? And if I take Laplace of this thing, it will come out to be RS is equal to 1 by S. Now we have standard transfer function CS by RS is equal to 1 by ST plus 1, right? So what I can do, I can take RS because we want system response only. So CS can be written as 1 by S upon ST plus 1, right? So I will separate these things using partial fraction method, or whatever method you may use that you might have studied in your mathematics course. Let me write directly 1 by S and minus 1 by S plus 1 by T, and that can be fraction like this using partial fraction. I hope you can solve. Now I am taking inverse Laplace transform of this thing. When I take inverse Laplace transform, I get 1 minus e to the power minus t by t ut for our causal system, right? So what I see, RT is my input, or this is like this thing. So if I talk in terms of causal system only, so this is 1 for all time, right? And if I see output, this is 1 for all time, and some part will be subtracting in this, and it will decay with time. So what happening is, this is called steady state response of a system, right? And this part consists of transient response. So it will die out with time, because it is exponentially decay. In 4 time or 5 times signal will be sufficiently decayed, and then we will be having steady state response, or whatever was the input that we will be getting as output, right? So first of all, its initial value, let's see its initial value. Its initial value is 1, and its initial value is 0, and its final value is 1. So how can I represent, like how can draw its characteristics? Like this is my step response, I represented by SR with respect to time, final value going to be 1, right? And here it is going like this thing, this is going like this, and as t tending to infinity it will go to 0, it will go on like this. But I cannot wait for infinite time to get a system to in its steady state value, so I have to tolerate for some tolerance in the system, right? For some period of time, like I was continuously talking 4 time constant or 5 time constant. That depends how much tolerance we want in the final output, right? So first of all, again I want to define time constant. So again I will take tangent of the system at t equal to 0. So how I take dct by dt is equal to I take this is going to be 0, and I'll be getting 1 by t e to the power minus t by t, right? And at t equal to 0, sorry, at t is equal to 0, and our slope will be dct by dt is equal to 1 by t, right? At t equal to 0 my slope is 1 by t, and this slope is 1 by t. Now I take its value as again x. This is going to be time constant. Let me show how it will be time constant. This value is 1, this value is 0, and divided by x minus 0. This is slope, and slope, what is slope? My slope is 1 by t, therefore x is equal to t. So this value is going to be t. Now what is the value of step response at this value? At t is equal to t, if I put again I get it like 0.63, right? So how can I define time constant in terms of step response? Time constant is defined as time taken. Time constant is defined as time taken by step response of a system to reach to 63% of its final value, right? Time constant is the time taken by step response to reach to its 63% of its final value. That's it. That's the definition of time constant. In terms of impulse response we have defined, and now I have defined this in terms of step response. This is very important thing, that's why I have taken time to define this thing. Now let's solve one problem. Like first is given this is ts is equal to transfer function, it is given s plus alpha, this is given, and input I have given with unit step function. Input is given unit step function, right? And it is asked to find k and alpha of the system, right? And step response is shown like this and like this. This is 1, this is our step response is shown here, and this is given like this. This is response going, and this value is given, this is tangent given, and this is 0.2, right? How do we solve? Now we know that in step response at which time tangent is drawn at t equal to 0, and this is my point 0.63, and this value is nothing but my time constant, right? So from our discussion of first order system, we know that time constant is nothing but inversely proportional to pole. And what is pole here? Alpha, right? So alpha will be equal to 1 by t, and when it is 1 by t, so I can write 1 by 0.2, therefore alpha comes out to be 5, right? So and last thing, we have given transfer function cs by rs is equal to k as alpha value I can put 5, and cs is equal to k, rs I can write ut as 1 by s into s plus 5, right? Now what I do, we know from final value theorem that limit s tending to 0 as cs is equal to final value, right? So what I can final value of this step response is 1, so what I can write is limit s tending to 0 as cs is nothing but k upon s into s plus 5 is equal to 1, right? So this s and this s will get cancel out, and when we put s equal to 0, therefore we get k is equal to 5, right? So that's how we obtain the value of k and alpha, and we can put this in terms of ts, and we can obtain our what is transfer function. So that's how we deal with questions, and now we will discuss some of the important things in our this graph, right? So first of all, for first order system we will discussing for first order system with step response, right? So actually this is given our this will be giving our steady state value of the system, and we are interested in steady state, how much time it will take to reach to up to some value, and how much time it will take to final value, what is tolerance, what is steady state error. These things we want to discuss. So I'm drawing step response here, little bigger picture. So let me write like this. This is from 50%, like 0.5, and this is say 1, and this is say 90%, 0.9, and here it is 0.63. I denote some of the important point. I am denoting step response, right? And here it is also 10% of final value 0.1, and this curve will go like this, and this tolerance will be there. Now first thing I need to define is delay time. Delay time means how much delay it is step response is giving to respond. Generally we take some value, it is not standard, but we take some value which we can see that effect is coming, like 1 is its output, then up to 10%, like 0.1, I can say that up to 10% is that value when I have started getting response from the system, that our system is started responding. So before this I cannot measure or something like that, so we take this as delay time. So this I defined as delay time, right? So I write it as TD. So I can, sorry, that was not, sorry, not 10% but 50%, I mean to say. That is the permissible limit, not this limit. TD, delay time, from 0 to 50%, because before this value, if we talk in terms of our if we use digital circuits for switching or something, that is the above, like we are taking an average value. So that is delay time. that is 50%. So delay time is the time taken by step response to reach to 50% of its final value, right? So what I can do is Ct is equal to 50% of 1 at t equal to td. So what I can do is I can put Ct is equal to 1 upon minus td by t is equal to 0.5, right? If I manipulate these things, I'll get td is equal to 0.693 t, or approximately equal to 0.737 t, right? 50% time taken by step response to reach to 50% of its final value, that is defined by delay time. This comes out to be 0.7 t. This is standard, you can remember, no need to derive it again and again. So let me now second thing comes out to be rise time, right? Rise time we take it as 10% to 90%, right? So this is our rise time. So how I define rise time? Rise time is the time taken by step response to rise from 10% to 90%, right? Rise time is the time taken by step response to rise from 10% to 90%. That's how we define rise time. So how I obtain, I can get Ct at t equal to tr is equal to I will calculate t1 for which step response is my 10% or it is 0.1, like so. How I can do minus t1 by t is equal to 0.1, and this comes out to be t1 equal to 0.1 t, right? And at t equal to t2 my response must be 90%. So if I calculate that thing, minus t2 by t is equal to 0.9, and after solving what I get is t2 is equal to 2.3 t. Now rise time is what? Difference between 90% value time and 10% value time. I can write t2 minus t1, so this I will get 2.2 t. So rise time will comes out to be first order system is step response 2.2 time constant, right? A time constant was RC, that you can take, but generally we will talk in terms of t. Now third thing comes out to be settling time. Settling time means the time taken by step response to reach to its 100% of final value and stay within that, right? But we have seen Ct was coming out to be minus t by t ut multiplied by ut. So final value 1 will be attained as t tending to infinity, but that is not practical. Time tending to infinity, what that mean? We transient will not die completely, but we need to have some permissible value, right? So if I take at t equal to 1 time constant, right? So output will reach to its 63%, right? 63%. So how much will be tolerance in output and input difference? Will be 37%, like that is very huge. 2t like 86% comes out to be, and 14% tolerance will be there. Third time constant will be 95% and 5% tolerance will be there. 4 time constant, it will be 98% and 2% tolerance will be there. 5 time constant is 99.3% and approximately 1% tolerance will be there. So generally we will accept these this kind of tolerance, 1% or 2%. Why? Like we need to have output 1 and its 1% come out to be 0.999 comes out to be. So these things we can accept. So generally we can take 4 time constant or 5 time constant. That will be given in exam. You cannot generalize like 40 or 50. You need to check what is given. 2% tolerance is permissible or 1% tolerance is permissible. That you need to look at, right? So that complete our discussion of settling time. Last thing comes out to be, here fourth thing comes out to be steady state error. Steady state error. Now what steady state error? Like we have taken some permissible value here, like in settling time we are talking about 5 time constant. Let's take this is our 5 time constant. This is not up to scale, but I am taking it as 5 time constant. Now 5 time constant means output is like 0.99 and but I desired is 1. So this is called steady state error, right? Steady state error will be denoted by ESS. Like ESS is difference between the desired output and the output obtained in that permissible value. 5T is like sufficient tolerance we take. So 5T is sufficient. So there will be some error. So how can I define error? Error is equal to ET RT minus CT, what output I am getting. So if I have to define like steady state error will be limit t tending to infinity and this is ET, and that's how we define steady state error of the system. Now steady state error is equal to limit t tending to infinity, ET is nothing but RT and RT is nothing but UT minus CT. CT is nothing but e to the power minus t by t UT, right? Steady state error, this t tending to infinity, right? So limit t tending to infinity, what I get is e to the power minus t by t UT, and if I put t tending to infinity, steady state error is coming out to be 0. Like that has to be the case because we have seen this system as t will tending to infinity, it will tend to 1. So in that case steady state error will be 0, but at this permissible value there will be some finite steady state error, but that's how we define in steady state. So in steady state it's going to be 0. Steady state error going to be 0, right? And now let's talk about speed of response in terms of its time constant. Speed of response, right? Say as t tending to decrease, if our time constant decrease, then we have seen delay time is directly proportional to t, right? Rise time directly proportional to t, settling time also directly proportional to t. Now as t tending to 0 decreases, TD, TR and settling time decrease. These are the important characteristics in time response analysis. How good a system responds, how quickly a system responds, right? So if these decreases, then I can say my speed of response increases. If speed of response increases, that is good. Increased speed of response, like curve will go like this, right? But speed of response has increased, but time with time increases, bandwidth also increases. Like bandwidth is inversely proportional to t, right? If my bandwidth increases, then noise increases. Noise increase, like if noise is increased, if that's why if noise is increased, then this system is not good. Its stability is decreased, because if noise is increased, stability has been decreased, right? So that is bad thing. So what I can say, that speed and accuracy of system are inversely proportional of a system, right? Sorry, stability in sorry, not stability, accuracy, because if noise has been increased, then I may not be able to identify my response. It will be like maybe like this thing, right? So accuracy has been decreased. So what I can say, that how to comment about stability, that if time constant has been decreased, that is poles are moving away, right? This is a time constant, say this is t1 and this is t2. Now t2 is greater than t1, right? If t2 is greater than t1, now this is nothing but pole, right? So this is inversely proportional to time constant. Now t2 is greater than t1, that means time constant associated with t2 is less, right? So if time constant is less, then stability is increasing, because we know as poles move away from this imaginary axis, then stability will increase. But stability is increased, accuracy also decreased, right? So we can say stability and accuracy are inversely proportional, right? So that's how. Why? Because if time constant decrease, poles move away from the imaginary axis, and as poles move away from the imaginary axis, stability of system increase. But moving away of poles mean time constant decrease, and time constant decrease means bandwidth increase, noise also increase, accuracy decrease, right? And this stability and accuracy, speed of the response depend only on the system, because time constant is nothing but RC, our element of the system, right? I think time is over, so we will conclude our discussion here, and in tomorrow lecture we are going to see our ramp response, parabolic response. They are very small topic, and then we will proceed to second order system. Okay, thank you.